First concept. I think I've said this already, but we only cover 3 concepts in calculus. Limits, derivatives, integrals. And that'll fill up our whole year. Limits is by far the shortest. It only takes about 2 weeks, and then we spend the rest of the year doing derivatives and integrals. Okay, so, works better when you turn it on. There we go. Numerically and graphically. So we'll start with the graph. After we do the you should be able to. Okay. Estimate the limit numerically and graphically. That's why it's called numerically and graphically. We're going to talk about what happens when you can't take the limit. We're going to talk about the formal definition of limits. That's where some of you will throw up. And then, as a safety tip, try not to get your brain melted today. Okay? So, limits. What is a limit? So let's look at that picture. I've got some function there. What can you tell me about that function, Cassie? Other than it's pretty.
It's got a hole in it.
It does have a hole in it. What generates that hole, by the way? How do you normally get a hole in a function?
It's the denominator 0.
Close. Because if the denominator is just 0, it generates an asymptote. So how does an asymptote turn into a hole? Yep.
If there's something at the top of the numerator and the denominator that cancels out.
So it's a thing on the bottom that gives you a denominator of 0 but also cancels on top. Okay, so we're going to start talking about a limit. And a limit in simplistic terms is what y value is the function approaching as you get very close to some x value. So let's look at something like 4. As x gets close to 4, what y value do we get close to? 2. Any problems there? No. Okay. What happens when we get close to 2.5, which happens to be where that hole is? What happens to the y value? One possibility is it doesn't exist. There's a hole there. There's no value. How can it be? By the way, is that a function?
Yes.
Yeah, okay. Just want to make sure we're on the same page. One possibility is that it doesn't exist. Since there's no value there, we can't have a limit. We're done. But that's not the case. And that's why we're creating limits, is because limits talk about what happens to the function as we get very close to that value. How big is that hole? That seems like a stupid question, but... And don't tell me it's about that big. No. Nope. Anybody else? Well, I use a hole to represent a certain amount, but in calculus we talk a lot about infinity. Infinitely small, infinitely large. That hole is infinitely small. So I can get really close to it, but not actually get to the value. So the question is, as I come sliding along the graph from moving from left to right, I'm getting very close to the point, to the y value of 1.5. Does everybody see that? Okay. As I go along here, as x gets bigger, this is getting closer. It's going up and up and up and getting closer and closer to the value of 1.5. As I come from the right, it gets closer and closer and closer to that 1.5. We'll pretend that's not there. To that value of 1.5. But it never reaches that 1.5. And so the problem that people get when they start talking about limits is they want to know, or they equate the value of the limit to the value of the function. They're not the same thing. Limit by definition is what value does the function approach as you get close to whatever x value. Okay, does that make sense a little bit there? Okay, so I got a bunch of examples for you. Let's look at this function. First of all, the notation there. LIM means the limit. So here we're talking about the limit as x gets close to 4 of that rational function. And there's a nice set procedure to do these problems, which is commonly referred to as an algorithmic approach. Do this, do this, do this. First step you should always do is plug and chug. You might want your calculators, by the way, if you want to bust those out. And you're going to be doing some, I don't know how good you are with mental math. let's start with the old plug and chug. So put 4 into that function and see what you get. I'm sorry it's so warm in here today. I don't know why. We must not have paid the air conditioning bill.
What is this?
Sorry?
What are we plugging into the?
4.
Oh.
Wait, what is stored time?
All right, what happens? 0? 0. 0? I'm sorry, what?
0 over 0.
0 over 0. 0 over 0, not same thing as 0. Are we all in agreement there? Right. 0 over anything other than 0 is okay. That's 0. But if you bother checking the bottom, you also get 0 over 0. That is never good. I don't care what math class you're in. That's not acceptable. All right. So that didn't work. What do we try next? Well, graph it. See what it looks like. Make sure when you graph it, you put the top and the bottom in parentheses so it graphs prettily. That's a word. See if maybe the graph will help you. Also a little bit of calculator practice for you, those of you that are rusty. Let's, of course, have your calculator skills up over the summer. Yeah, I figured as much. John, can you describe what you got there? Uh-huh. And what's happening, it's hard to see on that calculator, but what's happening at 4?
The line getting closer to the x-axis.
Uh-huh. Well, not the x-axis. The line x equals 4.
Yeah.
See what I'm saying? This side's coming up like this. This side's going down like that. Where's that happening? That's happening at x equals, I think it's -4 though, right?
Yeah, negative.
Is it -4?
I think so, yeah.
No, it's more. The original height. It's a whole. Well, you just hit
-4. So where's that asymptote, John? That's not, it's 4, it's on the negative side, right? Okay, now we got a problem. Hold on, this is so confusing. I've got this function, and I want to figure out what's the y value when I get really close to 4. So I plugged it, well, I didn't, you did. You plugged in 4 and found out that doesn't work because we get 0 over 0, and 0 over 0 is never a good thing. So then I asked you to graph it, and I confused John by saying the wrong things. We've got an asymptote over here somewhere, right? It's over on the negative side. And then it goes, is this right, John? Something like that?
Crosses the x-axis.
It crosses the x-axis somewhere?
On the left side.
Here?
Yeah.
Yeah, okay, that's right. Because we're concerned about over here at 4. So according to your calculator, everything looks peachy keen at 4, right? So go to the table. Error at 4. But the graph looks okay. That's the problem with the graphs on these TI calculators, is that they're not very accurate because you got these big honking pixels. We want like some 4K calculators, then we'd be able to see it. We don't have it. We've got some schlocky like, Game Boy type calculators here. So we can't see that. So since you're getting an error on the table, Molly, what do you think's happening at 4?
That's 0 over 0.
Good. What would that look like on a graph? What can't we see on the graph?
A hole.
Yeah. There's a hole there somehow. My point being, that calculator wasn't much help, so now we have to try something different. And what are we going to try? All right, so we tried plug and chug, it didn't work, we get 0 over 0. It doesn't matter on day 1 of limits or in May when you're taking the test. Anytime you see a limit, the first thing you should always do is plug and chug. These limit problems will get very complicated. There's nothing more frustrating than spending 10 minutes on a limit problem when all you had to do is plug the stupid number in. Okay, so try that every single time. This one, it doesn't work. Okay. So, as we said, let's factor it. So go ahead, factor. Figure out how I got there from what we had before. A little bit of factoring skill for you. If you factored correctly, you should end up with an x minus 4 on top and an x minus 4 on the bottom. Yes? They cancel. That generates our whole. What can you tell me about the denominator in the stuff that's left? What can't x be? Okay. Say again, I'm sorry.
I was gonna say the answer, and then I should just speak. My voice sounded really raspy. But
Yeah, was that ready to like,
I was like that.
Like you were possessed all the way.
Yeah.
yeah, I think you have to go back. Where is she?
Was she possessed or was she Batman? I don't know. That would be good.
Where's the acetone?
Heavy speaker.
If we looked at the graph before from what John helped us with, then we would get that negative 3/5, which would be why that asymptote is there. We don't care anything about that because all we care about is 4 and there's a hole there. So now plug and chug again. I got rid of the hole. Now I'm looking at a different function. If I algebraically simplify it, I'm changing the original rational function into something a little bit simpler. And I can plug and chug again, because now the hole is gone. I'm looking at a different function. When I plug and chug, I get a nice pretty answer of 15/17. Okay, so what does that mean? That means that that infinitesimally small hole that I have is located at 4,15/17. We just can't get to it from the original function because it doesn't allow us to plug 4 in. And again, we're not looking for the value of the function, we're looking at the value that the function approaches as we get very close to that value. Okay? Here's the fancy calculus speak. We've had this already. The limit as x approaches some number of a function is equal to what we commonly call capital L, which is the limit value. Remember, the a term is the x value, capital L is the y value. All right, so before we move on, how are we doing with the concept of limits? Good, bad, or still confused? Where are we at? This is the audience participation part of the program. Okay, I mean, you're not going to be able to teach the lesson, but you're not also running out of the room screaming. Okay, good. Here's another illustration of what I talked about. I've got some function and I can approach either from the right or from the left. This problem, or this picture, it doesn't matter because there is a value at the function. Those are boring. Those are the ones you're going to get when you plug and chug. It's just going to spit out the answer. But when there's something there, like an asymptote or a hole, something that you can't get a value from, then you have to start thinking about it in a different way. What about this guy? Let's take an algebraic approach first. What do you do first in any limit problem? Plug and chug. And when you plug and chug, you get...
Undefined.
Why is everything there said?
Undefined.
Undefined, because you have 0 in the denominator. Not good. Okay, graph that. You should know what that looks like, but if you need help, graph it on your calculator. See what it looks like. From your vast source of pre-calculus knowledge, you should realize that there's an asymptote at 0. No holes in this one, just an asymptote. And it's that double curvy thing. Pregunta, senor?
Yeah,
See?
when I'm graphing, like, it turns out, like, really odd. Like, in the example, it's like,
Oh, are you in, check your mode
yeah,
to see if you're in function.
All right, so it looks like that, yeah? All right. What's the limit as x approaches 0 then? We plugged and chugged. That didn't work. Next step is algebraically simplify that. Can you simplify 1 over x? No, not that I know of. So now we got to try something different. So let's look at the picture. As I get close to 0 along the x-axis, what's the function approaching? What y value is it approaching? What did you say, Ashley?
Positive and negative.
Positive and negative infinity. How can it be both?
If you do it from the right and the left.
So if I start at 8 and start walking along the function to the left, I'm going to go up to,
Positive,
and if I start at negative 8 and start walking to the right,
negative.
okay, so from the right-hand side it goes up to infinity, from the left-hand side it goes down to infinity. But that doesn't tell me what happens at 0 then. So what do you think it is at 0? Exactly, it doesn't make any sense, right?
Yeah.
Good. It's exactly what we needed. So in order to have a limit, we have to have this scenario. So now here's some new notation. What Ashley said is, okay, instead of just looking at the limit at the point, let's go from the left-hand side. That's what the A minus means, coming from the negative direction. So start walking along the graph from the negative direction and see what happens as you get really close to that value. And you told us that was negative, excuse me, special time in my life. You told us that was negative infinity. The other notation then is what happens when you approach A from the right-hand side, from the positive side, and that one goes up to positive infinity. Those two numbers don't match. If those two numbers don't match, then this doesn't work. You can't have a limit at the point. Okay, so now we get two different scenarios. One scenario is where you'll always have left and, I shouldn't say always, most of the time you'll have left and right limits. You might not have a limit at the point though, because you have to check, does the left side match the right side? If it does, then the whole thing works. Okay, are we good? That's a buzz phrase you're going to hear me use a lot. Left-hand limit must match right-hand limit. Left-hand limit coming from the left, right-hand limit coming from the right. Okay, so let's try this guy. We got a parabola with a hole at 1, 3, as shown at the right. There's the graph. Let's pick something simple. Let's do, before we get into this, let's take a look at the limit at -1. So, what is the limit as x approaches -1 of f of x? Okay, so we're gonna just stay away from that scary hole over there. We're not gonna go anywhere near it. I'm just gonna go way over on this side and talk about that. This guy right there. Doesn't have a limit.
No. Yeah.
Yes? What is it?
One.
Why?
You can plug in.
It's a classic plug and chug. Out -1, there's nothing weird going on, it's just part of the graph. So plug and chug, you put in there, you get -2 over -2, 1, done. Okay, easy. Okay, now let's do this. What is the limit as x approaches, what are we doing, 1? Yeah, 1 from the negative side. Here I am at 1. I'm sliding along the graph here, and as I'm going up and up and up, I'm getting closer and closer to what value? 3. I'm not getting to 3, I'm just getting closer and closer. Let's go from the other side. Now I'm over on the right-hand side, sliding down this parabola, getting closer and closer to x equals 1. What is the y value getting closer and closer to? 3. Oh, look. The left-hand side matches the right-hand side, so therefore, what is the limit at the point 1? 3. Okay, since they match, everything's good. Even though there's a hole there, we don't care. Does that make sense? Okay, everybody good? So then we should probably look at one where it doesn't work. Bump, 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 dump, bump. Yep, we got that. Okay, good. Yep. All right. How about this guy? To be honest, I don't know if I included a graph. I did not. Just for giggles, try graphing that on your calculator. I have no idea what that looks like, but the graph might help a little bit. More craziness. You get the same thing, get a little curvy thing and a little. How come you got that thing down? Yours looks different. Half of a sideways parabola, yes? Okay. Well, what happens when you approach 0? Does that thing even come all the way over to 0? No. Wait, yours crosses 0? Does yours cross 0? Yours crosses 0. Yours is different too. Molly, Jack got the same thing. You might have typed it in wrong?
Yeah, I did
Didn't close parentheses or something?
No, I did X -1 in the.
Okay. So we can look at we can go through the same process we went through before. Look at the graph. Well, the graph doesn't tell us much because again, we're on the Schlage TI graphing thing that's not going to show holes and stuff like that. There might be a hole somewhere, who knows? We'll figure that out. Or you can look at the chart and see that at 0, you're going to have an undefined term. What we want to talk about, though, is what's happening when we take the limit. So I've got a couple charts here that show you what's going on as we get closer and closer to 0. So notice on each side of those values, I'm approaching this point 0. And I'm increasing the detail as I get closer and closer to 0. And you also see that the points are getting closer and closer to 0. So in calculus, we don't talk about things like 1.1. That doesn't matter to us. That's way too big. We start talking about things like 0.0001, 0.000001. And as we get more and more accurate, as we approach that value of 0, the answer is going to get more and more accurate, so we get a value of 2. Now, the question is, how are you going to find that value of 2? You're not going to sit down on a test and make a little chart and start plugging in numbers. How do we take that equation, or that function, and figure out that the value of the limit is 2? Well, what's the first thing you do?
Plug, check.
Plug and chug. What happens when you plug 0 in there?
Undefined.
Undefined. How do you algebraically simplify that monster if you can? This will be a good algebra practice. Here's some geometry for you, in case you wanted to refresh your memory. Okay, so it's x over the square root of x plus 1?
Yeah.
Minus x plus 1, then minus 1. Okay. Can I algebraically simplify that? You could rationalize it, which is exactly what you need to do here. I would multiply by something called the conjugate. Does that term ring a bell with anybody? Square root of x plus 1 over the square root of x plus 1 plus 1. Well, that's going to get a little nasty. I'm going to leave the top alone for a second. What does the bottom become? X plus 1 minus 1, which becomes, that cancels, the square root of x plus 1 plus 1. All right, does everybody see how I got to that? When you're multiplying out the denominators, the reason we choose the conjugate is because they're the same thing with opposite signs. So it's like multiplying a plus b times a minus b. The middle term drops out. So I took the first term times the first term. The middle term disappears. I took the last term times the last term, and I end up with that thing down there. Plug and chug, it didn't work. Algebraically simplified. Plug and chug again, what do I get? So what is the limit as x approaches 0 of this function? 2, which is what we expected to get. Gesundheit. Yeah.
Where'd you get the plus 1?
What's your question again? You're good? Okay.
Wait, the conjugate is like reverse sign?
I'm sorry?
For the conjugate, you did plus 1, is that what you?
Yeah. Yeah, the conjugate of a plus b would be a minus b. You just change the sign in between the two. That's what you should have seen on your calculator. Zoomed in on a decent graph. More pictures. I went the wrong way. Okay. Limits that failed to exist. This is, I don't know, I guess I can just ask. Have you seen this graph before? Yeah, other than in this class. Did you do this at all last year in pre-calc? Okay, that's going to be one of our mother functions. The absolute value of x over x is the same thing, by the way, as x over the absolute value of x. They like to get crazy and flip it over. It graphs to look something like this. The values are always 1 or negative 1, depending on whether you put in a negative value or a positive value. So let's go through the steps again. What is the limit as x approaches 0 from the positive of that function? What do we got? Hmm? 1, correct. Why, mine?
So you go from the right towards zero.
Good. Perfect. As I go from the right, as I get closer and closer to 0, the x value of 0, I stay on that y value of 1. Okay, so what's the limit as x approaches 0 from the negative side of the same function? Negative 1 from the left-hand side. So therefore, what's the limit as x approaches 0? Good. DNE does not exist. Because, and you'll be asked to justify this. So the problem will say something like, find the limit as x approaches 0 of the function. Your answer would be DNE, but then they'll say justify your answer. Your justification is very simple. The left-hand limit does not match the right-hand limit. Left-hand limit does not match right-hand limit. You'll be justifying almost everything, and that's a justification for that particular problem. The other thing that'll happen is, no problem. Scared me, you're like a ninja, I didn't see you coming. They'll change that value. In that particular graph, 0 is what I call the funky point. It's where the weird stuff happens. I could also ask the same problem and just change the 1 to, let's say, or change the 0 to a 2. Okay, what's the limit of this function as x approaches 2? Well, here's 2. As I come in from the left, I get a value of 1. As I come in from the right, I get a value of 1. Therefore, the limit is 1. Done. Okay, that's a plug and chug problem. The absolute value of 2 over 2 is just 1. What you have to be aware of is when they choose those funky points and how you're going to handle those. Okay, so we did all that. Here are 3 scenarios for you. Things that cause problems. Well, first one we pretty much beat into the ground. Left-hand limit doesn't match the right-hand limit. Increases or decreases without bound as x approaches c. What's that in English? What does the term decreases without bound translate into? Nope. Negative infinity, very good. If it approaches infinity or negative infinity, there's no limit. Even if they approach the same thing. Okay, this causes problems sometimes. Let's suppose I've got a function here, and this one comes up and goes like that, and this one comes up and goes like that. Coming from the left, I have an answer of infinity. Coming from the right, I have an answer of infinity. So therefore, the left-hand limit matches the right-hand limit, must be infinity. No, infinity is not a number. That would be does not exist. Okay, then 3 is the weird one that pops up every once in a while. So sometimes we'll have these oscillating functions, sometimes called a dampening function, where as you get closer and closer to 0, it just continues to bounce up and down. If it never gets closer to one particular value, it can't have a limit. 3 is not that important because it doesn't happen very often. However, 1 and 2 are going to show up all the time. Okay, you ready for this? There's Kleenex up here if you start to cry. It's really not that bad. In fact, just put your pencils down. Just be mathematical sponges and absorb the information here. All I'm looking for you to be able to do is hold a somewhat intelligent conversation about a formal definition of limit and understand the terminology that I'm going to use in order to justify these limits. Okay? I'll try to make this as painless as possible. We talked about this stuff already. Okay? In the formal definition, for some reason, they switched the a's to c. So as x approaches c of some function, you get this value of L. Okay? Nothing new there. What is new is they create something called a neighborhood. And this is how the neighborhood works. They pick some value around C, and they go a little bit to the left and a little bit to the right. And you can see that illustrated in the picture. You see C, and then I move to the right and to the left, and I add a little bit. I don't know if I mentioned it here, but I did, yeah. Do you know what a Greek letter that is? That's a lowercase delta, right. So you move over a little bit to the left and a little bit to the right. Now, how far do you move over? It's up to you. This is where it gets a little weird. You choose how big delta is. And by choosing a delta, it's going to generate some areas around the limit answer. Okay. Those values are called epsilons. And when you take those epsilons and those deltas together, you end up creating this little rectangle. This rectangle goes something like this. Let's go here and here. Okay, so there's our rectangle. That rectangle is made up of adding deltas on the x values, adding epsilons on the right values. Now, what makes the limit exist is that if your values stay within the neighborhood. Okay, well, this seems silly. What does that mean? I mean, there's my value right there. That guy's inside the neighborhood, therefore I'm good to go. Okay. So one argument would be, well, if I make my deltas really, really big, then I can include everything in the neighborhood. But they should be, by definition, very small values, because in calculus we work with very small things. So how does this work for us? So let's go back to one that we know doesn't work. Where is that guy? Here. So we'll talk about why this doesn't work using the epsilon and delta idea. So we're going to talk about at 0. In around 0, I'm going to add a little bit of deltas on both sides. Something's fairly small. So I'm going to come a little bit over here and a little bit over here. So that's my positive delta, and this is my negative delta. And I get vertical lines here to generate two sides of the neighborhood. Then I go up to my limit value there, my capital L, and I choose a couple epsilons. All right, I'm going to take a small epsilon here and a small epsilon there. So there's epsilon and there's epsilon. I get this, bring that across. And therefore I have my neighborhood now. My neighborhood is this yellow region, which everything seems great. The reason it seems great is because my answer is right inside that neighborhood. However, there are also some values down below that are not in the neighborhood. This stuff right here. So over this entire range of deltas, you've got to have all your x values and your y values inside the neighborhood for it to have a limit. Okay. Like the example I talked about before with this 2. If we were taking the limit here at 2, I'd create some deltas, come up here, create some epsilons, come up here, there's my neighborhood, and the entire graph from negative delta to positive delta is inside the neighborhood, so we're good to go. All right? Could you speak somewhat intelligently about a delta? Yes or no? Do you understand what an epsilon is? Could you draw a neighborhood? You're golden. Because what we don't want to do is go back to this, which is start generating equations with absolute values with epsilons and deltas in it, and then start simplifying those to end up with that mess. We don't care about that. There's your 6-step approach for trying limits. 5 is optional depending on your views. 4 might not be a bad way to go also. I left off step 5.5 would be cheat off your neighbor. Okay. What's that? What did I forget?
Not sacrifice yourself.
ones, yeah, that's another one. Yeah, that'll come later though. You'll need that for later. So tomorrow we'll go over day 8 to get that wrapped up, which is a review for chapter P, so then we'll be done with that until Friday for the test, and then continue on for ourselves. I was planning on doing it today, but I'll give it back to you tomorrow. Wait, hold on. Stop talking for a second. They are graded. I haven't set up Infinite Campus yet. Normally, as soon as I get them graded, I dump the scores on Infinite Campus so you can find out how you've done. Because I haven't set up Infinite Campus yet, I'm not able to do that, so I apologize. But again, they're done. I'll give it back to you first thing tomorrow. We'll talk about them together.
Where are they?
Ooh, what about Treat Tuesday? Great question. So what we'll do is we'll postpone